Hi, this is Bob Pryor. Today I'm talking to you about graphing sine and cosine functions. We're going to start with the sine function, and we're going to call it f of t equals sine of t. And we're taking the values from around the unit circle. You'll notice that the second row there are the radian measures around the unit circle, starting with 0 and then pi over 6 and pi over 4, and I have the quadrants listed above. And we know that in quadrants 1 and 2, the sign is positive. And in quadrants 3 and 4, the sign is negative. Well, I'm going to put down a couple of axes, a horizontal and vertical axis, and we are going to connect those sine values. Very familiar to you, 1/2 square root of 2 over 2, square root of 3 over 2, 1 and 0. And I'm going to connect them all, and this is the form that we get for the sine function. We're going to be learning a lot more about that in this lesson. And here is the same type of chart, but this time for f of t equals cosine of t. Again, everything's coming from the unit circle. The quadrant values, where cosine is positive in quadrants 1 and 4, negative in quadrants 2 and 3. And you can see how we have all the cosine values and just connect them. And this is the basic graph of the cosine function. Now here again, looking at a closer look at the sine function, just from 0 to pi, we see that we have we know that sine is 0 at 0 and at pi, and sine is 1/2 at pi over 6 and 5 pi over 6. And it's square root of 2 over 2, which is approximately 0.7 at pi over 4 and 3 pi over 4. And sine is square root of 3 over 2, which is about 0.85 at pi over 3 and 2 pi over 3. And at 90 degrees, or at pi over 2, the sine is 1. And here's we see for the cosine function, which starts off at 1 when at 0, and then at pi over 6 is square root of 3 over 2, again about 0.85. And at pi over 4, it is square root of 2 over 2. And we can see how the cosine values are working their way down to be 0 at the 90 degree mark, pi over 2. And then in quadrant 2, we think of the quadrant 2 values of cosine. We're now looking at the negative values. 3 pi over 4, 5 pi over 6, those are quadrant 2 values on the unit circle, and they show up as negative in this plane. So we don't really have to graph all of them. What are the most important points? Well, they're the ones that give us the zeros, the maximums, and the minimums. And you'll notice that what I have circled there are the axial radian measures. We do the same thing for the cosine. The axial radial measures are the ones that are the most important for the cosine function. And we see that we're only putting dots at the max, 0, and min. So you notice that maybe the sine and cosine are actually very similar in a lot of ways. In fact, if we don't have a vertical axis, you can't tell whether this graph is a sine function or a cosine function. All it tells us is that the characteristics, the features, are identical. And when we draw, we need to make sure that we're using concavity correctly, that we have upward concavity when the graph is below the t-axis, and we have downward concavity in green when it's above. And every time it hits a 0, it switches concavity. And those are called points of inflection. Now, one complete cycle of a graph goes from possibly a maximum to a maximum. Here I'm drawing forward, backward, it doesn't really matter. One complete cycle could be from a 0 to another 0. Not the very next 0, but a 0 to 0. We could even have a complete cycle from a minimum to a minimum. And notice that a cycle ends exactly where it begins. Let's talk about the period of the function. This is an important feature that is true for both sine and cosine. And it's a horizontal axis distance, meaning along the horizontal axis, whatever is one complete cycle. So if we go from a maximum to a maximum, from 0 to 2 pi, that distance is the period. So 2 pi is the period. Here's a different pair of maximum to maximum, but again, the period will be the same. This time it's 4 pi minus 2 pi, but again, the period is still 2 pi. And if we go from a minimum to another minimum, in this case from pi to 3 pi, again, the period will be that difference, which is 2 pi. You'll notice that it's very consistent for a particular graph. The period will not change for an individual graph. We could even go from a 0 to a 0. These are non-consecutive zeros. There is a 0 in between, but we've got to make sure that it starts and ends at the same location, in the same direction as well. Again, we subtract one from the other and we get 2 pi. So let's practice that. Here I have a graph of one function or the other. I don't know which it is. And it's the cycle that starts at pi over 6 and ends at 5 pi over 3. So the period is the difference between those two values, 5 pi over 3 minus pi over 6. And we need to get a common denominator, so we multiply by 2 over 2. And we see 10 pi over 6 minus 1 pi over 6 is 9 pi over 6. Simplifies to 3 pi over 2. And that's the period of that graph. I'll leave the other one up to you. Another important feature is the frequency. And it is the number of complete cycles between 0 and 2 pi. And it actually also appears in the function. It's the coefficient of the argument. So, for example, if our function is f of t equals cosine of 5t, then the frequency is 5. The coefficient is 5, the frequency is 5. F of t equals sine of 2/3 t, the frequency is 2/3. Let's see how that plays out on an actual graph. Here we have f of t equals cosine of t. It starts at a maximum and ends at a maximum. It goes from 0 to 2 pi. So that is the period, 2 pi minus 0. Notice that the coefficient of t is 1, and that the period, 2 pi, could actually be thought of as 2 pi divided by that frequency of 1, which is, again, 2 pi. Here we have one cycle complete between 0 and pi. You can see that being drawn here. That's the end of the first cycle, so automatically that's the period, from 0 to pi. But going to 2 pi, we actually have a second cycle. And so there are a total of 2 cycles between 0 and 2 pi, so the frequency is 2. And we can see that 2 in the coefficient of t. This time the period is pi. In this graph, we actually have 3 cycles. We see the first going from 0 to 2 pi over 3, and that automatically is the period. But the frequency is how many cycles we can get in between 0 and 2 pi. So far we've got 2 cycles, and of course here comes the third cycle. So again, the frequency is 3 because there are 3 cycles between 0 and 2 pi. And we even see that 3 as the coefficient of t in the function. 2 pi divided by the frequency is 2 pi divided by 3, and that is the period. Now let's take a look at graphing the sine function, called the parent sine function, f of t equals sine of t. You'll notice that it starts at a 0, at the origin, 0, 0. And we're only using our unit circle axial values along the t-axis, and that's what generates our max and mins and zeros. And here I am carefully drawing in each segment so I can make sure I have good concavity. And I also put something a little bit on the right and a little bit on the left to indicate that the graph could go on in either direction. So let's practice working with the concavity and points of inflection by tracing this sine function that came from a graphing calculator. You can see that, again, I'm just piecing things together so I can have good concavity. There's a change in concavity, a point of inflection, at every 0. And at each end, on the right end and the left end, I include a little extra to indicate that the graph could go on. Now here we see the parent cosine function, f of t equals cosine of t. And again, just using the regular axial measures on the unit circle, we're generating those important points on the graph of cosine. The max, the zeros, the mins. And once that's ready, we piece it together and also add a little bit on the right, a little bit on the left to indicate where the graph would be going if we continued. One more thing, note at the bottom here that the argument inside, we could use any variable. We've been using t, we could use theta or alpha, but we're going to start using x now. Okay, so here we have some characteristics that are common to both sine and cosine. The first is the amplitude. It's the measure above the x-axis, basically from a 0 to a maximum. And because it's a distance, it's always positive. We've talked about the frequency. The frequency is the number of complete cycles from 0 to 2 pi, and it's the coefficient of x in the function. We've talked about the period. It's a distance along the x-axis of one complete cycle. And for the parent functions, it's 2 pi. And the y-intercept we sometimes refer to as the starting point, though really the graph can go to the left and to the right forever, so there's no real starting point. But usually we think of the y-intercept as that. And the sine begins at a 0 at the origin, and the cosine begins at a maximum. These are for the parent functions. Now, how do we find points along the x-axis? I have two techniques. One I call the half and half technique. And so what we recognize is that after x equals 0, there are 4 evenly spaced major x values. The first one we usually mark is the period. So that's got a 1 next to it. That's the first thing that we'll mark is the period along the x-axis. Then we'll recognize the half period. Then the quarter periods. And then we'll find the 3/4 period by multiplying by 3. Notice that the 3/4 period is 3 times the quarter period. And the half and half part comes in finding the half period and then taking half of that to find the quarter period. These together are called the featured x values. So let's say that we have the period already appearing on the x-axis. We're going to use this half and half technique to find the other 3 featured x values. Step 1, of course, is to identify the period. Step 2 is to find the half period. And that means taking the period 3 pi, multiplying it by 1/2, 3 pi over 2. Step 3 is to take half of that. That's the quarter period. 1/2 of the 3 pi over 2 gives us 3 pi over 4. And then the 3/4 period, this is the 4th step, we find by multiplying the quarter period by 3. 3 times 3/4 in this case to get 9/4. And those are the featured x values for this function. This time, the period is 4 pi over 3. So after we identify that, the half period is half of 4 pi over 3, 1/2 times 4 pi over 3, and we'll simplify that fraction to 2 pi over 3. Really what we did is we took half of 4, which is 2. That's another way we could have done this. Step 3 is to find the half. Again, halfway between 0 and the half period is the quarter period. And we see that that is at 1 pi over 3, or just pi over 3. And the last step is to find the 3/4 period. 3 times the quarter. And that's just going to be pi. The 3's divide out. Okay, a second technique for finding points or finding featured x values is using the standard counting unit, which I abbreviated as SCU. And it is the quarter period. So I've got that labeled on the first graph. That's the quarter period, pi over 6. What we're going to do now is actually count by pi over 6. 1 pi over 6, 2 pi over 6, 3 pi over 6, and 4 pi over 6. But on the x-axis, we'll write the simplified forms. So you see it's pi over 3, then pi over 2, and lastly 2 pi over 3. This is called this counting using the standard counting unit, SCU. Here the standard counting unit is 2 pi over 5. That's the quarter period. What we're actually going to be doing is counting by 2's. 2, 4, 6, 8. Notice that the numerator value changes, 2, 4, 6, 8, but the pi is still there and the denominator 5 doesn't change. We're really counting only by the numerator value, 2, 4, 6, 8. And that gives us our featured x values. This time we'll be counting by 3's. The pi will be consistent and the 8 will be consistent in the denominator. But we're counting the numerators by 3's, 3, 6, 9, and 12. Some of these do simplify, and we want to simplify the first to 3 pi over 4, and then the last to 3 pi over 2. Now you don't have to write them up above like I was. You can simplify them in your head, that's fine. So now what we're going to do is use both methods to generate all the featured x values on the x-axis. Knowing what the period is, we'll be able to find each of the values that come before the period, the half period, quarter period, 3/4 period. And then we identify the standard counting unit, always the quarter period, and we then count from 2 pi onward. Well, the standard counting unit is pi over 2, so the 2 pi is 4 pi over 2, and that begins the series 5 pi over 2, 6 pi over 2, 7 pi over 2, 8 pi over 2. Now, if you're able to do some of this simplifying in your head, you don't need to write all the values that I have below. When you are finished, though, you should notice that the very last value, the end of the second cycle, is 2 times that of 2 pi, where the end of the first cycle is. Let's do this again. We have 8 pi over 3, half period, half of 8 is 4, so 4 pi over 3. Half of 4 is 2, so 2 pi over 3. And then when we multiply the quarter period by 3, it becomes just 2 pi. And now we use that quarter period as a standard counting unit. Step 5 is to count along the x-axis. We ended the first with 8 pi over 3, and now we count by 2's. 10 pi over 3, 12 pi over 3, 14 pi over 3, 16 pi over 3. And we double check to make sure that the ending value, 16 pi over 3, is twice the period, 8 pi over 3. Again, we find the half period using the half and half technique. Then we find the quarter period. In this case, half of 3 pi over 8 will be 3 pi over 16. And then when we multiply that by 3 to find the 3/4 period, it's 9 pi over 16. When we start our counting, we think of 3 pi over 4 in terms of sixteenths because that's the standard counting unit. So we start with 12 pi over 16, and then we add 3 to the numerator over and over until we get to the end. Some of these will simplify. 18 pi over 16 simplifies to 9 pi over 8. And the last one simplifies to 3 pi over 2. Again, we double check to make sure we did a good job and make sure that the ending value, 3 pi over 2, is twice the period. Okay, so now we're going to graph two cycles of the parent function f of x equals cosine x. We're going to identify the amplitude and the frequency and the period. The amplitude is 1 of the parent function, and the frequency is 1 cycle from 0 to 2 pi. And of course, the period is 2 pi. We've seen that already. We could also use that formula, period equals 2 pi divided by frequency, which is 2 pi over 1, still 2 pi. Now, because we'll be graphing two cycles, we want to locate the period halfway down the x-axis on the right, 2 pi. Then use the half and half technique to find the half period, the quarter period, and then the 3/4 period. We also must identify the y-axis values for the amplitude, maximum at 1, and then goes to the 0 at pi over 2, and then to a minimum. And then you can see that, 0 and maximum. And then here we are putting in the different segments. And a little bit more on the left, just a little bit to indicate where the graph is going that way. But on the right side, we still have to do one more cycle. And so we locate 4 evenly spaced marks for the next 4 featured x values. As you see there, the standard counting unit is pi over 2, and after 2 pi, it's 5 pi over 2, 6 pi over 2, 7 pi over 2, and 8 pi over 2. And now we'll put in points to fill in the second cycle, the 0, minimum, 0, maximum. And then we'll put the segments in. And a little bit more on the right. And there's our graph. That's 2 cycles of cosine of x. Let's do the same thing for sine of x. Again, we've already seen amplitude is 1, frequency is 1. This is the parent function. And period is 2 pi divided by the frequency. 2 pi over 1 is 2 pi. So we locate 2 pi in the middle of the x-axis, and then do the half and half method to find the half period, and the quarter period, and the 3/4 period. We find the y-axis values, max of 1, minimum of -1, but the sign starts at the origin and then goes to a maximum, then to 0, then to minimum, then back to 0. And that is one complete cycle. We draw in the segments. A little bit more on the left, going downward. Then we draw in the 4 marks along the x-axis for the second cycle. Again, 5 pi over 2, 6 pi over 2, 7 pi over 2, and 8 pi over 2. Then we locate the points. We have maximum, 0, minimum, 0. Same as the first cycle. And we put in the segments. A little bit more on the right to show where the graph is going afterward. And there is our parent function, 2 cycles of the sine of x. Okay, now we get a chance to talk about modulated sine and cosine functions. Notice the a times the sine of bx. A represents the amplitude, and it is the coefficient of the whole function. And because amplitude is a distance, it's always positive. So a itself could be negative. We write the amplitude as the absolute value of a. However, if a is negative, then the graph is a reflection across the x-axis. The frequency as before, is the coefficient of x, the b in this case. And the period, again, is the x distance of one complete cycle. So we have a formula for the period, 2 pi over b. Before we said it was 2 pi over frequency, but of course frequency is b. Now the y-intercept we often call the starting point, although there's no real true starting point for a sine or cosine function. It's usually where we start drawing the graph. And for the sine, it's the origin. And for the cosine, it's at 0a, which might be a maximum, or could be a minimum if a is a negative number. Let's put these into action. Here we're going to graph two cycles of f of x equals sine of 2x. We see the general form now, f of x equals a times the sine of bx, and we see that the a is 1, and that represents the amplitude. And because a is positive, there's no reflection. The value of b is 2, that's the frequency. And to find the period is 2 divided by the frequency. 2 over 2 is pi. We locate pi halfway down the x-axis, do the half and half method to find all the x-axis values in the first cycle. We'll locate the y values, that represents the amplitude, the max and the min. And then because this is the sine function, it starts at the origin, then goes to a maximum. Then to 0, minimum, 0. We put in the segments. Then we put 4 marks on the x-axis to the right, so we can put in the second cycle. And here you see the quarter period is pi over 4, and so after pi, we count 5 pi over 4, 6 pi over 4, 7 pi over 4, and 8 pi over 4, which is 2 pi. After the 0 at pi, we go to a maximum, a 0, a minimum, and a 0. And then we put in the segments. And as before, a little bit to the right, we continue the graph, and a little bit to the left, we continue the graph. Okay, let's take a look at a cosine function. We see here that the value of a is -2. That means the amplitude is +2, because amplitude is always positive. But there's a reflection this time about the x-axis. We'll see how that plays out in a moment. The frequency this time, the coefficient of x, is 2/3, so the period is 2 pi divided by 2/3. We treat that as 2 pi over 1 times 3/2. And we see here the 2's divide out, and we get just 3 pi. We locate 3 pi halfway down the x-axis, and then we use the half and half technique to find the half period, the quarter period, and then the 3/4 period. The amplitude is 2, so we mark 2 and -2 on the y-axis. And because this is a cosine function, it starts at 0a, which actually, because a is -2, it starts at a minimum. And then we progress to 0 and to maximum, to 0 and minimum. And then we draw in the segments, and a little bit to the left. And then we're ready to make marks along the x-axis for the second cycle. This time the quarter period is 3 pi over 4, so that's our standard counting unit. And 3 pi itself, where we ended, is 12 pi over 4. And if we now count by 3 pi over 4, that means adding 3 to the numerator. 15 pi over 4, 18 pi over 4, 21 pi over 4, and finally 24 pi over 4. And we'll mark those values along the x-axis in simplified form. (24 pi over 4 is 6 pi. And just to double check, that's twice 3 pi. After the minimum at 3 pi, the graph goes up to a 0, then a maximum, a 0, and a minimum. And then we can put in the segments. And we'll go a little bit to the right to see where the graph would continue. Okay. Well, this is graphing sine and cosine functions. I hope this has made sense and has been helpful to you. I'll look for you next time. Take care.